Okay, now we're going to talk about a specific convention tool, Denavit-Hartenberg representation, that is going to explain how we can convert the transformation matrix from the zeros join to the end effector of the robotic device. So when we are using this specific method, there are four parameters we need to consider. Those four parameters are divided into two groups. The first group is the coefficient of the robot, and the second group is the coefficients between two joints. And they are corresponding to rotation, which is theta, and distance between joints, that is going to be defined as d. And also we got the joint offset, that is going to be defined as a. And also we got twist angle, which is defined as alpha. So let's talk about those kind of things a little bit. So I got a specific joint. Let's say this is joint 0 and this is joint 1. And this one is going to be twisted a little bit. And this one is going to be connected to another robotic device, which is a job. So we might attach X, Y, and Z at the first joint. And we define the second joint over here, Z1, X1, and Y1 over here. So this one over here, when it starts to rotate, that is going to be my device of the rotation. And this distance is going to be the distance above it. So this one has nothing to do with the x-axis along this direction. So the d in this case is going to be 0. But when we connect this one to this one, we actually has a distance that is going to be a between those two joints. That is going to be my joint offset. And if this one has some force that make Z1 and Z0 are not in parallel, but they are twisted a little bit, then we need to define the angle alpha over here. In this case, since we both got thickness over here, so the distance between this one and this one can be defined as my d over here. So those are the four parameters that we need to deal with to calculate the transformation matrix from joint 0 to joint 1. When we combine everything all together, we still follow the rotation matrix and the transformation matrix we derived in the previous part of this module. But we need to put all the matrix into a specific sequence before we can obtain the transformation matrix. The first one is going to be uh, about the axis, and this is about the rotation, which is theta. So if we know that there is an angle theta over here, and that is going to be about the axis, then this is going to be the first transformation matrix we need to put over here. And if this joint over here has some kind of a distance between itself and the next linked joint, then that is something we define as my d, and this is going to be a translation since this is pure distance. After that, the linkage between the first joint and the second joint got some kind of joint offset, which is along x-axis. Then we're going to use translation matrix to represent the, excuse me, the translation matrix between joint 0 and joint 1. Again, after that, since we know the z-axis or the bar has been twisted a little bit, so z1 and z0 is no longer in parallel. In that case, we also need to have some kind of a twist angle and its corresponding rotation matrix defined. So combine all those four matrices all together. This is something we're going to um, do the calculation for the transformation matrix. Now, how do we define all the terminologies over here? So those are the four coefficients that we're going to define using our method. So this one over here defines the angle between the two links, which is along the axis. This is important. When you are defining those four matrices, the coordinate or the direction must be following the definition over here. The first two must be along the z-axis. The third one and the fourth one, they must be about x-axis. Those are important. So if we know there are some kind of offset between those two joints and they are on along the z-axis, you must define that as your d. If you start to rotate about z-axis, it is about to rotate about a specific axis, that axis must define as your z. Now, since we know there is a distance between the first joint and the second joint, this direction over here must be your x-axis, and the distance between those two joints, we define that as our a. If you got some kind of twisted angle between the first joint and second joint, then the twist angle is defined as alpha. So those are important definitions we need to remember when we start to define the coordinate system for a robotic device. Because if you are not using this specific definition of four transformation matrix, we are not be able to communicate with other people, because those are the common languages people are using in robotic area and in animation area. Okay, so let's talk about what we're doing over here. So, okay, before we start to talk about those kind of things, there are a few rules we need to remember while we're dealing with those kind of things. The first one is right hand rule, which is something we defined earlier. Right hand rule is use the right hand and use 3 fingers, your thumb, your index finger, and your middle finger. This one over here is always Z. This one over here is always X. This one over here is always Y. So when you are drawing your coordinate systems, those are 3 directions you need to follow. You cannot just define any coordinate system you want to, because it doesn't make sense when you are communicate with other engineers or animation designers. There must be right hand rule, because it's a space, and pretty much you can define X, Y, and Z based on what you want to do. But when you are designing those kind of things and you want to talk with other people, then you must follow X, Y, Z, use your right hand so other people know which direction you're actually talking about. And this is important for all the transformation metrics. Now, since we talk about those kind of things, there are many other things we need to know. Based on what we know earlier, is that we got 4 coordinates, 1 rotation and 1 translation along or about the axis. They are theta and d. And there is another angle and translation that is corresponding to x-axis. They are a and alpha. This is translation. If you got a joint over here, this must be your z, and this must be your theta. This one between the first joint and second joint, this must be my x. So y is going to be defined. And at the second joint over here, you put another joint over here. The distance between those two, that's your d. And after that, the relationship between those two z-axes, that's going to be my alpha, and the distance over here, that is going to be my a. So it will be a good idea, since we have multiple joints and we have multiple links. So it might be a good idea that I'm going to define everything. Link 1, 2, 3, 4, dot, dot, dot. And all the 4 coefficients, A, alpha. This group is going to be x-axis, and I also have d and theta. This is going to be my group of z. So if we can identify all those things all together and put out all the four matrices over here, then we should be able to find out the transformation matrix from the first joint, from the first link to the end of the robotic device. And this is going to be important. We need to follow everything that defined using DH convention. So again, then you might find out, okay, I know those rules, that's fine, I know the definitions, but how do I decide the x coordinate, x direction and z direction at the specific joint? This is something we're going to do. There are two rules that we need to know. We need to know how to define the x direction and z direction. The first rule is that x and must be perpendicular to the previous z direction. So use this configuration over here as my example. This is my n+1 joint, and this is my n joint, and this is my n-1 joint. So the x, this one over here, certainly we are having another z over here. But since z might not be aligned well, so they must be have some kind of angle of alpha. But the the x direction over here must be perpendicular to two things. My current z-axis that's given because that's the definition of coordinate system. Meanwhile, it must be perpendicular to the previous z-axis. That's another one. Second one is if you define the x direction over here, it is going to be intersect with the previous z-axis as well. Only when you can fulfill those two conditions, you're going to define your coordinate systems for individual joints or individual links in your system using DH convention method. This is important. So one of the first thing you wanna deal with is to define your coordinate system for individual links using DH. So finding what is your x, what is your z, that will be important to get the correct transformation matrix from the beginning till the end. So keep in mind, this is something we need to do all the time. Okay, now we're going to talk about the examples.